Okay, that was the last example for that notebook. Key points. The Spark UI, and let me refresh that tab. It's because we were using the higher level API, we have the details over here, and everything else looks exactly the same as in case of the data frame. Just because we were using the case class and we were defining what data structure we are expecting, we achieved the type safety, and that's really the big difference. Okay, that was the last example for that notebook. Key points to remember, guys. The first one is RDD, which stands for Resilient Distributed Dataset, and it's immutable distributed collection of objects, which helps Apache Spark to achieve the fault tolerance, data lineage, and support a wide range of transformations and actions. Just the RDD API is not the most intuitive, as we have seen it. The second data structure is called the data frame, inspired on pandas from Python. And data frame is a high-level abstraction over RDD, organizing data into named columns, similar to the tables or to the spreadsheet. And whenever we are using a data frames, everything goes through Spark Catalyst Optimizer, which is a big benefit. And the third data structure is called dataset, and this combines benefits of RDD and data frame, offering a strongly typed object-oriented API. That's why we can use it only in Scala and combine it with the optimization capabilities of the data frame. Let's talk about the transformations and actions. So basically in Apache Spark, there are two types of operations you can perform. It will be either transformation, either action. Transformation can be understood as a business logic you want to apply to your data. It takes one or more RDD, data frame, or dataset and transforming it into new. We were already repeating multiple times. RDD data frames and datasets are immutable. So whenever we want to do something with the data, it will create a new one. The original one will not be changed. Let's talk about the transform and combine it with the optimization capabilities of the data frame. Let's talk about the transformations and actions. So basically in Apache Spark, there are two types of operations you can perform. It will be either transformation, either action. Transformation can be understood as a business logic you want to apply to your data. It takes one or more RDD, data frame, or dataset and transforming it into new. We were already repeating multiple times. RDD data frames and datasets are immutable. So whenever we want to do something with the data, it will create a new one. The original one will not be changed. And transformation, this is important, can be either narrow, either wide. Wide transformation requires shuffling data between the partitions, meaning exchange of the information between the executors. And example of the narrow transformation are filter, select, create new column, or cast. So let's say that we have a data distributed across multiple executors, and we call a function filter. Executors don't have to exchange any information between themselves. It will be enough if each executor will just filter a data which is having in his own memory and return the results. There is no need for exchanging the data. On the other hand, the examples of the wide transformations, such as group by, sort, and join, those require shuffling the data. And again, we can imagine data spread across multiple executors, and we calling a function sort. Then, in order to have a data properly sorted out, it will not be enough if each executor will sort only data which is having and then return the results, because data will be partially sorted. There need to be exchange of the data between the executors. So there need to be something which is called data shuffling happening, so we can sort all the data properly. And the last thing about the transformations are lazy by nature, meaning Spark will not do anything unless it will have to. And on the other hand, we have actions. Actions is a demand of results. For example, whenever we are calling a function collect, count, save, take, and show, this is basic information for Apache Spark. Okay, enough is enough. Execute all the transformations plus an action I have been asked you to do, and Spark will not wait any longer. It will execute everything what we have asked Apache Spark to do in our application. And we are in the third notebook about the transformations and actions, which are another cornerstone of Apache Spark architecture. And this is the shortest notebook we are having. We are having here only one query just to demonstrate the difference when we are having only transformations and when we are applying an action. So right now, we are reading the data which we already know about New York City taxis, and we are applying our first transformation filter, and then we are applying our second transformation, which is select of two columns, and then we are doing the group by and some calculation. So this could create the impression that we are actually calling for an action, but at this stage, we are not telling to the Apache Spark. So right now, we are reading the data which we already know about New York City taxis, and we are applying our first transformation filter, and then we are applying our second transformation, which is select of two columns, and then we are doing the group by and some calculation. So this could create the impression that we are actually calling for an action, but at this stage, we are not telling to the Apache Spark what do we want to do with the data. So if we run that, no computation will be kicked off. There will be, however, one small job over here, job number 47, with one stage, which will be super fast. It took 1 second or less. This job is not about the computation. If we look inside of that job, we will see that this job is really for a Spark to figure out what data we are talking about. It's not even about reading the data, it's just about figuring out how to partition that. So let me close that. And for the comparison, here we are having a three simple actions: show to display raw results to the screen, count to count the records. And the third one is actually more interesting. It's about writing the data. But in this case, we are not going to write anything anywhere because we are specifying format noop, which is sort of fake. It's an information for Apache Spark that we are doing that just for the testing purposes. We don't want to save any data to the storage. And let me uncomment one of it, and the difference will be noticeable. While previously it took less than 1 second, right now it will take way more, and we can already see that we have more jobs. We have the same job as previously about figuring out the partitions, and then we are actually having the heavy duty job with the real computation. And now the whole application took 57 seconds because only now the data has been read and the calculations have been executed, and that's it for that notebook. Job stages and tasks. So every time we supply application to the driver will split our application into one or more jobs. Jobs can be run in parallel, but it's under some circumstances, but usually it will be run one after another. Inside each job, we have one or more stages. What is important to remember is that stage 2 can happen often more the time we supply application to the driver will split our application into one or more or jobs. Jobs can be run in parallel, but it's under some circumstances, but usually it will be run one after another. Inside each job, we have one or more stages. What is important to remember is that stage 2 can happen. Only can start only once the stage 1 will be finished. There are, again, some special cases where they can slightly overlap, but the general rule is that stage 2 will start after stage 1 will be finished. And inside each stage, we have multiple tasks, or one or more, and we can run as many tasks in parallel as executors CPU code. Of course, that we already know. And the reason for stages to happen one over another is because Apache Spark tried to compact all the transformations which does not require data shuffling into one stage. So all the narrow transformations like a filter or creating the new code. And we can run as many tasks in parallel as executors CPU course that we already know. And the reason for stages to happen one over another is because Apache Spark tried to compact all the transformations which does not require data shuffling into one stage. So all the narrow transformations like a filter or creating the new code. And then only when the data shuffling is required, then the new stage will be created. So the data shuffling is a boundary between the stages. And now, each job is represented by some something what is called directed acyclic graph. In short, DAG. And it's called like that because it's only one direction. And in this case on the right, we have example, very simple example of DAG with two stages. Stage number 10, then the data shuffling is happening, and stage number 11. Even we have here information that the exchange is happening. So this is also information for us that the data shuffling is happening over here. And before seeing that in practice, let's discuss one more time laziness of Spark. So let's say that we have very simple application, which is reading some data, and already at that stage, Spark will or can fire very small job to figure out which data we are talking about, where are the files, what files we are talking about, how much data there is. And let's say that in our application, we want to group by something this data, and then perform another wide transformation, maybe sort, maybe join, and then filter the data, and then we are asking Apache Spark to show us the results. So Apache Spark is smart enough to identify this guy and to figure out that it will be way more efficient to push that guy as much as possible to depth. And the reason being is by doing that, Apache Spark can limit the data we are reading. Maybe data are being partitioned, maybe instead of filter, we are using a select and data are in packets, so Apache Spark will only read instead of this to show us the results. So Apache Spark is smart enough to identify this guy and to figure out that it will be way more efficient to push that guy as much as possible to depth. And the reason being is by doing that, Apache Spark can limit the data we are reading. Maybe data are being partitioned, maybe instead of filter, we are using a select and data are in packets, so Apache Spark will only read a specific columns, but basically Apache Spark will try to limit as much data as possible. So the further transformation, the wide transformations, will have less job to be done. And then, of course, show is happening, so action, and Apache Spark will fire jobs, in our case, job number 1, and second job number 2. And this laziness of transformation is one of the principles of Apache Spark architecture. And we are in the fourth notebook, jobs and laziness, and second job number 2. And this laziness of transformation is one of the principles of Apache Spark architecture. And we are in the fourth notebook, jobs and laziness according to Apache Spark architecture. And this will be a combination of the things which we already know very well with some new stuff. So let's talk first about DAX. Here we have a query from the previous notebook where we are reading a data, applying a filter, select, doing a group by, and then an action show. And in our case, the query has been already executed, and we can figure out part of the DAC already starting from here. We see that we have 3 jobs and 4 stages. If we go to the Spark UI and we find, for instance, a job 63, we can figure out a DAC over here. So 63, and that's a DAC for that job. If we remember the RDD, we didn't have multiple jobs, but we had a one job with multiple stages, so we could see all the stages in one place. In case of the data frame, like right now, we have different jobs, and if we want to have the holistic view, we need to go to different stages and figure out the different part of the application over there, like to job number 65, and figure out this part of the DAC, or the DAC for this job over here. Another way on looking on the DAC is to the DAC for to job number 65. We have different jobs, and if we want to have the holistic view, we need to go to different stages and figure out the different part of the application over there, like to job number 65, and figure out this part of the DAC, or the DAC for this job over here. Another way on looking on the DAC is to go to SQL data frame tab. Just this time we don't get exactly a DAC, but something what is called a plan. And we already know plan very well. It looks like following, and the way we read it is from the figure out the different part of the application over there, like to job number 65, and figure out this part of the DAC, or the DAC for this job over here. Another way on looking on the DAC is to go to SQL data frame tab. Just this time we don't get exactly a DAC, but something what is called a plan. And we already know plan very well. It looks like following, and the way we read it is from the bottom, because that's the only way really you can do that properly. But if we scroll down, we see very, very interesting thing over here, details. And if we expand it, we see something what is a bit scary at the beginning, but it's actually very intuitive and useful. This is the post-execution details of what Spark has been done. Under the physical plan, we see what steps Apache Spark has been done. We also see the initial plan. The difference between that we will discuss in a moment when we'll be talking about the catalyst optimizer. And if we scroll down to the bottom, we see further details about the plan. And actually, what we see here at the beginning, it's very useful, but we don't need to wait for the execution to happen. We can actually figure out this plan and at the same time have a pretty good idea about that straight from the place where we are writing our code. And for that, we don't need any action. If I comment show, so we have only transformations, and I use a function explain, control enter, I'm going to get, well, one simple job because Spark is trying to figure out the data again, but then we are going to get a physical plan as Spark believes it will look like. And the way to read it is from the bottom again. So at the beginning, we are doing the file scan, and we can see that Apache Spark is trying to extract only the columns which will be needed for the computation. If we were using as a dataset a Parquet files or data format, Spark would be actually successful and would read only those columns. But because we are reading the CSV, Spark needs to read the whole dataset anyway. Then Spark. So at the beginning, we are doing the file scan. And we can see that Apache Spark is trying to extract only the columns which will be needed for the computation. If we were using as a dataset a Parquet files or Delta format, Spark would be actually successful and would read only those columns. But because we are reading the CSV, Spark needs to read and would read. Way to read it is from the bottom again. So if transformations and I use a function explain, control enter, I'm going to get, well, one simple job because Spark is trying to figure out the data again, but then we are going to get a physical plan as Spark believes it will looks like. And the way to read it is from the bottom again. So at the beginning, we are doing the file scan, and we can see that Apache Spark is trying to extract only the columns which will be needed for the computation. If we were using as a dataset a Parquet files or Delta format, Spark would be actually successful and would read only those columns. But because we are reading the CSV, Spark needs to read the whole dataset anyway. Then Spark is applying our first filter over here, checking if the pass, because we are reading the CSV, Spark needs to read the whole dataset anyway. Then Spark is applying our first filter over here, checking if the path bottom again. So at the beginning, we are doing the file scan, and we can see that Apache Spark is trying to extract only the columns which will be needed for the computation. If we were using as a dataset a Parquet files or Delta format, Spark would be actually successful and would read only those columns. But because we are reading the CSV, Spark needs to read the whole dataset anyway. Then Spark is applying our first filter over here, checking if the passenger count, that's the filter, checking if the passenger count is not null, and checking if the passenger count equals to 1, as we've written in the query. Then we've written in the query select, and the same is happening over here, just it's called project, trip distance, and payment time. Then we see the first calculation, hash aggregate, so group by happening on the separate slots. We see exchange, and we already know very well that exchange is about the data shuffling. And then we see the final group by, and that's the whole plan as Spark see it before executing actually the query. Of course, it may happen that in case of the big complex applications, while the execution is happening, Spark will collect more data about the execution, and it will decide to change the execution plan on the fly. But in majority of the cases, this plan displayed with the function explain, this is actually fairly similar to what you are going to expect to see at the end of the execution. And let's now talk about the laziness. I just need to change comments over here. So this is the same query as above, and this is going to give us exactly physical plan as before. It's exactly the same. And now what I want to do is I want to add one more transformation over here, one more filter to the whole query. And here comes the beauty of the laziness. Because Apache Spark is not executing anything every time we are giving him a transformation, like here, here, or here, but waiting for an action, Spark will actually catch the fact that we are doing a transformation which he can push closer to the source, and he will optimize the query for us. Let me hit Control Enter, and let's see where this filter with payment type equals to cash will be pushed. So Control Enter. And as we can see, instead of adding the filter at the end of the execution, Spark is actually pushing that filter and combining that with the same filter as we have before, with the filter about the passenger counts. And now we are filtering not only passenger counts equals to null, but also adding payment types equal to null, and the same passenger count equals to 1, and payment type equals to cash. Apache Spark used the opportunity of being actually lazy, and before us hitting and adding any actions, it actually optimized all the operations we are expecting it to do. Let me add to this one more thing. The function explain is having actually very useful parameter, which is called true. And once you will be learning Apache Spark more and more, you will be using this function pretty frequently. Let me keep the same query and push Control Enter right now. The difference is that right now, besides of the physical plan, which I got before, I'm also getting other plans, the earlier plans. And if I scroll to the top, I see something what is called parse logical plan, meaning that would Apache Spark ask us if it wouldn't be lazy. It would read the data, apply the first filter, apply the first select, group by, and the function explain is having actually very useful parameter, which is called true. And once you will be learning Apache Spark more and more, you will be using the function pretty frequently. Let me keep the same query and push Control Enter right now. The difference is that right now, besides of the physical plan, which I got before, I'm also getting other plans, the earlier plans. And if I scroll to the top, I see something what is called parse logical plan, meaning that would Apache Spark ask us if it wouldn't be lazy. It would read the data, apply the first filter, apply the first select, group by, and the second filter at the top. That would happen if Apache Spark would execute the query as we are asking him to do. But because of the catalyst optimizer, which we'll be discussing later on, it was successful to go through a couple of optimization stages and push it closer to the source. That's it for that note. Data shuffling. So why do we care about data shuffling? We are talking about it pretty a lot. So data shuffling is a process of redistributing data across partitions and typically involves data exchange between executor nodes. We already know that. And wide transformations require shuffling, of course. So for example, whenever we have narrow transformation, and we can imagine that this is our cluster of executors, when we want to apply a transformation like a filter, which is narrow, each executor can take data, which is having already in memory, and just apply a filter. It doesn't need to have any other data from any other executors. And in contrast, when we want to perform a wide transformations like a join or sort or group by, then each executor to perform that task properly needs data from other executors, so we are exchanging the data. And the problem is that the beauty of Spark is because it's processing the data in memory. That's another fundamental principle of Apache Spark architecture, and that's why it's so fast. And whenever we are talking about the data shuffling, we need to take that data from the memory, save it to the storage, send it over the wire to again to the storage, and then again read it to the memory. And those operations are significantly slower than just in-memory processing. Sometimes you can avoid it, like for instance, avoiding making unnecessary sorts or optimizing some joins or filtering some data early on. Frequently, we shouldn't go crazy about the data shuffling. We should be aware of it. We should be aware when in our code it's happening, but just sometimes we will not avoid it. And before jumping into databricks, let's take a look at one more example. Let's say that we want to group by and count our data, and different colors represents different category of data. So at the beginning, driver is deciding on how to split the data into the partitions. Then each executor is grabbing their part of the data and perform a local group by and count. But shortly, executors are hitting the wall, and in order to continue, they need to do a data shuffling, so the new stage is required. The data is being exchanged, and only then executors are able to continue with their task and perform the final counts, and here comes the results. And we are in another notebook, this one about the data shuffling. And the reason we are here, well, actually there are three reasons. First of all, is to see how you can recognize a data shuffling in Apache Spark UI. The second reason is to see the impact of data shuffling on the performance. And the third thing is to see that the data shuffling does not only depends on the type of the transformation we want to apply to the data, but also on the data itself. So knowing the data is always a good thing. What is different is that most of the queries in this notebook has been already executed by me. It's because they take a bit of time and to make it faster. The data we are using is a data which we already know and like about New York City taxi. That's how it looks like. We will use a couple of columns like a pickup date, payment type, and fair amount. And the first query is follow. We are reading the data for 2 years, so we are going to get around 5 gigabytes. And then we are doing a very simple group by a payment type and doing a count. And if we take a closer look on the payment type, we are let's follow. We are reading the data for 2 years, so we are going to get around 5 gigabytes. And then we are doing a very simple group by a payment type and doing a count. And if we take a closer look on the payment type, we are going to see that we have only two options over here. Someone paid either by credit or by cash. And this type of the column is called low cardinality column because there is very few options. And if we run explain, then we are going to see no surprises over here that we are doing the file scan. Then we are doing the first group by, then exchange. And every time we see exchange, we already know what it means, data shuffling, and then final group by. And after executing the query, that's the query execution group by. And after executing the query, that's the query execution. The action is writing the data, but it's a fake writing because the format is nope. That's the results. We're having 3 jobs. And we can go to the Spark UI and take a closer look on those jobs and how to recognize the data shuffling. It was 3, 4, and 5. If we check the execution time, job number 4 was the one which took the most of the time. So let's go and see the details of it. And once I will scroll down, I can see over jobs. And after executing the query, that's the query execution. The action is writing the data, but group by, then exchange. And every time we see exchange, we already know what it means, data shuffling, and then final group by. And after executing the query, that's the query execution. The action is writing the data, but it's a fake writing because the format is nope. That's the results. We're having 3 jobs. And we can go to the Spark UI and take a closer look on those jobs and how to recognize the data shuffling. It was 3, 4, and 5. If we check the execution time, job number 4 was the one which took the query execution. The is writing the data, but it's a fake writing because the format is nope. That's the results. We're having 3 jobs. And we can go to the Spark UI and take a closer look on those jobs and how to recognize the data shuffling. It was 3, 4, and 5. If we check the execution time, job number 4 was the one which took the most of the time. So let's go and see the details of it. And once I will scroll down, I can see over here on the right, shuffle write. This is basically the information, how much data has been written to the storage, to the drive for the purpose of shuffling. This time it's not a big number. It's 125 kilobytes. And we can see further details by clicking on the stage description, scrolling down, and we also have a static. It's been written to the storage, to the drive, for the purpose of shuffling. This time it's not a big number, it's 125 kilobytes, and we can see further details by clicking on the stage description, scrolling down, and we also have a statistics. What was the minimum volume of data written by single task to the storage, and what was the biggest volume of the data written to the storage by a task? 86 kilobytes, so a bit more. And if we scroll down, we can also see the details by a task. So that was the task which wrote the most, and if I sorted the second direction, this wrote way less. Okay, let me keep the tab open, and let me scroll down to the second query. So here we are having exactly the same query. What is different is the column on which we are doing the group by. So previously we were grouping by payment type. Now we are grouping by fair amount. And if we look on the data, this is a higher cardinality column because we have way more options over here than a payment type. And again, checking the execution of that query, job 6, 7, and 8. So let me go to the Spark UI and find those jobs 6, 7, 8. 6, 7, 8. So job number 7 was the one which took the most of the time. Let's see the details. And we see that shuffle write, nothing big, 1044 kilobytes. And going into the details of the stage, we are probably going to see some small change over here. So the minimum was 40 kilobytes written by a task, and maximum was 50. Not a big deal if we compare it with the previous one. Well, more or less the same. We are still talking about very, very small number of data written to the disk. It's not rather anything impacting the performance. But let me now get back to the notebook and let's do exactly the same query, just this time using the pickup date time. And if we check the data, pickup date time, it's somewhere on the left, pickup date time. So we see that this is really the high cardinality column. There will be very, very, very few values which are like this one. Okay, this one is happening twice, but usually each and every value will appear only once. So this is the high cardinality column. And going back to our query, as the results, we got job number 9, 10, and 11. Let's find them in the Spark UI. 9, 10, and 11. So job 10 was the one which was taking the most of the time. And let's go into the details. Scrolling down, we see that this time we brought into the storage to the drive way more data. Before that, we were talking about 1 megabyte. Now we are having 673 megabytes. And this is significant value. This is the shuffling which we want to be aware of. So let's go into the details of the stage and scroll down. Well, first of all, we will notice that some tasks are having the yellow bar. And the yellow bar, according to the agenda, is the shuffle write time. And this is the indication for us that each task does not only spend a time doing the calculations, but actually the task started to consume a time on writing the data to the storage for the purpose of exchanging it. So we start to see the impact. And if we scroll down, now we are having pretty significant number of data written to the storage by each and every task, 24 megabytes over here, and on the right, 29 megabytes. And if we compare it to the previous one, previously we were talking about the kilobytes, and now we are talking on the megabytes. And here we have the example of the shuffling, which is actually already having the impact on the performance. Let's get back to the notebook and and if we scroll down, now we are having pretty significant number of data written to the storage by each and every task, 24 megabytes over here, and on the right, 29 megabytes. And if we compare it to the previous one, previously we were talking about the kilobytes, number of data written to the storage by each and every task, 24 megabytes over here, and on the right, 29 megabytes. And if we compare it to the previous one, previously we were talking about the kilobytes, and now we are talking on the megabytes. And here we have the example of the shuffling, which is actually already having the impact on the performance. Let's get back to the notebook, and I have one more query, and the last one in that notebook, and this is sorting. So sorting should be prohibited in data engineering work. So what we are doing here is we are reading the same data and then order by a trip distance. And then if I hit explain, what we are going to see similar query, file scan, exchange, and sort. And if I scroll down to the query results, that's how it looks like. It took 40 minutes to order it. So whenever we can avoid sorting data, that's something that we should do. And let's go and see the details of the job 13, 14, 15, and 16. We see actually 3 jobs, which took significant number of time. Let's check out the one which took the most, 16 minutes over here. So let me click it, scroll down. So only this job brought to the storage more data than we are reading from the file. It brought, for the purpose of shuffling, it brought 37 gigabytes. So you see how complex the shuffling can get. And let's get into the details by the curiosity to see how it looks like. And if I scroll down, well, we see that actually tasks it brought 30 data. Let's check out the one which took the most, 16 minutes over here. So let me storage more data than we are reading from the file. It brought, for the purpose of shuffling, it brought 37 gigabytes. So you see how complex the shuffling can get. And let's get into the detail. by the curiosity to see how it looks like. And if I scroll down, well, we see that actual tasks spend more time on writing the data to the storage for the purpose of the shuffling than the computation itself. So it's pretty impressive. And if I scroll down further, I see that the task which wrote the smallest number of data, it was already over a gigabyte, and the one which wrote the most of the data, almost 2 GB. Let's do one more thing and see how we can check the same in SQL data frame tab. And 13, 14, and 16, that's the one which is interesting, duration 30 minutes. Okay, so that was our execution plan. And if I go and check, let's see the exchange over here. And we see that shuffle bytes written total 37 gigabytes. And the total number of time the task spent on writing at the drive over 1 hour. So you see that how you can think of a kind of simple computation like the order by can generate a massive data shuffling, and what a big impact it can have on the performance. And before I will close that notebook, let me one more time pay attention to the number of the partitions. We are talking about partitioning of the data, usually twice in Apache Spark. First of all, when Apache Spark read the data from the storage, then we were talking multiple times that the driver check out the data and decide how to split it into partitions. But there is also a second moment when we are frequently talking about the partitioning of the data. It's when there is the data shuffling happening. The default number of the partitions when the data shuffling is happening is 200, meaning whenever we have data shuffling, Apache Spark will try to divide it into 200 partitions and distribute. And here, this is the introduction to the next part, which is about the optimization. We are going to see a mechanism which is deciding on the fly what's the optimum number of the partitions, not to keep it 200 all the time. And in our case, it has decided that the 4 number is the optimum number of the partition for the data shuffling. So it has decreased the number of the partitions, but more about that in the next notebook. Let's get back to the disk and to sum up everything. So we already know how to check a data shuffling in Apache Spark UI. We saw the impact on the performance, which can be tremendous, even with the simple operations like the group by. Similar case can come with the merge operation. And we also saw that the data shuffling does not only depend on the transformation, but also on the type of the data by executing the same query 3 times, just changing the type of the column from low cardinality column to the high cardinality column. Key points to remember. Shuffling is a process of redistributing data across partitions and typically involves data exchange between the executor's nodes. It requires saving data to the disk, sending that over wire again to the disk, and only then can be read into the memory, which of course is slow. Data shuffling can be very expensive, as we have seen. Sometimes it can be mitigated or avoided by even a code change, like for instance, avoiding sorting the data. Nevertheless, it's often necessary evil. Ladies and gentlemen, let's touch on the optimization topic in Apache Spark. And optimization in Apache Spark architecture, it's a massive thing. And you as the user can do a lot to optimize your flow. That will be discussed in separate movies, including choosing the right format to keep to store your data, like a Parquet or Delta format instead of the CSV, especially Delta format. It's so way more optimized than the CSV. Avoiding expensive operations like sort, which we already know that is generating massive data shuffling, minimizing volume of data, caching data frames, repartitioning, avoiding something what is called user-defined functions. Again, a separate movie about that will come. Partitioning or indexing data, bucketing, optimizing cluster itself, and so many more things, which we will discuss in details. Nevertheless, what is important at this stage is to understand that Apache Spark architecture is designed in the way to do a lot of things for us already, including catalyst optimizers, which we have mentioned a couple of times already, but also something new, what is called tungsten, which we didn't touch on, and we will say a couple of words about it, or adaptive query execution, which also works for us a bit in the background. Talking about the catalyst optimizer. Whenever we have a SQL query or some code using data frame or dataset, the first thing which is generated, it's called unresolved logical plan. And the first step for the catalyst optimizer is to check if the tables we are using in our query or the code, columns or functions, are actually being registered in the catalog. If they are not registered in the catalog, we will get an error. If those exist, logical plan will be generated. Then catalyst optimizer is doing a couple of things for us, like a post unfolding. So if we are having some constant in the code, it will replace it in the values, or predictive pushdowns or projection pruning, meaning pushing filters and select as early as possible to minimize volume of data is being read, and it's generate optimized logical plan. And with a couple of things for us, like a cost unfolding. So if we are having some constant in the code, it will replace it in the values, or predictive pushdowns or projection pruning, meaning pushing filters and select as early as possible to minimize volume of data is being read, and it's generate optimized logical plan. And with optimized logical plan, it's generate different possibilities to execute that plan, including different strategies to perform joins, and then calculates the cost model for each of it, checking how much data will be read with each physical plan, how much network movement will be done, or how complex computations are. So it calculates the cost model for each physical plan, and then it selects the most optimum physical plan, and voila. Tungsten, it's a bit of different beast. The goal of Project Tungsten is to improve Spark execution by optimizing Spark jobs for CPU and memory efficiency. So Catalyst Optimizer, as we have seen before, generate optimized execution plan. Tungsten, on the other hand, it's used to generate optimized code using full-stage code gen, which we have seen many times in the execution plan already, and improve how the data are being handled in the cluster. So comparing to the Catalyst Optimizer, Tungsten optimizations are just way closer to the bare metal. And the last theory before jumping into databricks and seeing things in action is called adaptive query execution. And this is actually a very interesting optimization approach, which makes sure that your application is not optimized only once at the beginning, but once your application runs and Spark collect more and more information about the data, about the operation, about the cluster behavior, it reruns some elements, recalculate the optimizations, including Catalyst Optimizer. So the Catalyst Optimizer will not be run only once at the beginning of your application. It only once at the beginning. Sure, there is the of Spark execution by optimizing Spark jobs for CPU and memory efficiency. So Catalyst Optimizer, as we have seen before, generate optimized execution plan. Tungsten, on the other hand, it's used to generate optimized code using full stage code gen, which we have seen many times in the execution plan already, and improve how the data are being handled in the cluster. So comparing to the Catalyst Optimizer, Tungsten optimizations are just way closer to the bare metal. And the last theory before jumping into databricks and seeing things in action is called adaptive query execution. And this is actually a very interesting optimization approach, which makes sure that your application is not optimized only once at the beginning, but once your application runs and Spark collect more and more information about the data, about the operation, about the cluster behavior, it reruns some elements, recalculate the optimizations, including Catalyst Optimizer. So the Catalyst Optimizer will not be run only once at the beginning of your application, but if the application is long enough, it will be run multiple times. That's why sometimes we will get multiple jobs, and in each job, we have only one stage, because after that one stage, adaptive query execution was triggered, the Catalyst Optimizer recalculate everything once again, and that has created a new job, which we are going to see that in a second anyway. And this will involve dynamically change sort merge into the broadcast hash joins, dynamically decrease number of the partitions, dynamically handle skews, dynamically detect and propagate anti-relationships. And we are in the optimization notebook. We are going to see in actions three main optimization mechanisms in Apache Spark architecture: Catalyst Optimizer, and adaptive query execution, and a Tungsten project. Not all the details, but enough so we can understand the concept. So starting with Catalyst Optimizer, we have spoken about Catalyst Optimizer quite a bit already. And we know about its lazy evaluation feature, and we saw it in action. Here we have another feature in action, which is called predictive pushdown. So already here, before executing the query, Apache Spark has figured out that it would be way better for everybody if we could read from the storage only the data about the fair amount, because nothing else is being used. And the example of how this is happening is over here. Apache Spark is doing this predictive pushdown by trying to read from our files only the fair amount column. Just in this case, we are keeping the data in the CSV. CSV is a row-based format, therefore there is no really option to read a specific column. That's why it's way better to keep the data in Parquet or in data format, which is fairly the same. Both of them are column-based types, and in such a case, Apache Spark could actually read only the specific column which he would need for the computation, like over here. Moving forward, adaptive query execution. So let's at the beginning turn it off, and we can turn it off just for the purpose of the demonstration. In the production, there is no purpose of doing that, by setting up the variable Spark SQL adaptive enable to false. And if we run our query, this is what we are going to get. And I'm curious if you are going to spot the difference, because we were running that query already before. So we got two jobs, 18 and 19. Let's see how those looks like. So job 18 and job 19. So it's over here. The one which took the most of the time was job number 19, and seeing the details. So for the first time, we can see two stages in the job connected with each other, stage number 23 and stage number 24. So we are scanning the file, having the whole stage code again, which is the result of the Tungsten project. We will talk about it in a second. Then we have the exchange, and we are reading the data and doing another computation. And if I scroll down, I see details for both those stages. So below we have stage number 23, and we see that we have read around 11 gigabytes of data. Then we see that we have a shuffle of write. So we've wrote 23 and stage number 24. Just think how those looks like. So job 18 and job 19. So it's over here. The one which took the most of the time was job number 19, and seeing the details. So for the first time, we can see two stages in the job connected with each other, stage number 23 and stage number 24. So we are scanning the file, having the whole stage code again, which is the result of the Tungsten project. We will talk about it in a second. Then we have the exchange, and we are reading the data and doing another computation. And if I scroll down, I see details for both those stages. So below we have stage number 23, and we see that we have read around 11 gigabytes of data. Then we see that we have a shuffle of write. So we've wrote to the disk around 1 megabyte of the data. And then a second stage starts, and we have read also around 1 megabyte of data. So we wrote it, and we read it in the next stage. What is interesting is that we have 200 tasks over here. So going into the details of stage number 24 and seeing 200 tasks. So, and that's how it looks like. And we have all colors of the rainbow. And those are our 200 tasks. So actually, the reason for having 200 tasks is because the data by default are being partitioned into 200 partitions when they are shuffled. And without the adaptive query execution, there is no mechanism in place to consolidate those and to request Apache Spark to minimize the volume of it. And if we see on how the tasks spend their time, is we have here orange, and orange is shuffle with time. Here we have a green, we already saw green before, and we have some blue, scheduler delay. We have some orange, and orange is task-based serialization time. So you see what's happening without adaptive query execution mechanism turned on, which is pretty recent. And if we scroll down, we see all the details for all those tasks. We can also go to the SQL data frame tab and find the same job number 19, which is over here. And let's check how this looks like here. So what is different is we don't have anymore a block which was representing action taken by the adaptive query execution. Therefore, we are doing the exchange. We are partitioning the data into 200 partitions, but there is again no mechanism to decrease the number of the partitions. If we take as the comparison the previous query where the adaptive query execution was on, like this one, we are going to see that we have the exchange, we had 200 partitions over here, but we have adaptive query execution shuffle read, which collapsed that into the 4 partitions. So that's one of the big difference. Another difference will be visible once we will turn it on. So Spark SQL Adaptive enabled true and run exactly the same query one more time. You can probably already see a next difference. Here we're having 2 jobs, 18 and 19, and here we are having 3 jobs. The reason being is that adaptive query execution, as the name suggests, it's something what is being used by Apache Spark during the runtime, which it means that it's not anymore just run like Catalyst Optimizer at the beginning of the query, but it's being run between the jobs, and it can trigger Catalyst Optimizer one more time or collapse the number of the partitions, and that happens over here. As we can already see, there is no stage including 200 partitions, and checking job 20, 21, and 22. So let's get back to the SQL and the data frame tab. 21, 22, that's the one. We can see exactly the same schema, just this time with collapsing the partitions from 200 into 1. In our cases, we are not using the massive volume of the data, so the difference in the performance may not be so visible. But on the production, if you try and turn it off, you will quickly appreciate it. Okay, let's now talk about the tungsten project. So tungsten, as we spoken, is way closer to the bare metal. Focus of the tungsten project is to introduced a set of optimizations into Apache Spark architecture related to the memory usage optimizations or a CPU usage. One of the example of the tungsten in action, we will see if we will turn it off. And we can turn it off, or different parts of it, we can turn it off. And here we are turning off the optimization, which is about generating optimized code for each and every task. So if we run exactly the same query without tungsten project turned on, and we go and check job 23, 24, and 25. So let's open this one more time, and jobs 23, 24, and 25. And as usual, taking the one which took the most of the time. What we are going to see, we don't have here anymore whole stage code again. Instead, we have hash aggregate. If we compare it with previous jobs, like this one, then we can remember that always previously we were having the whole stage code again. It means that Tungsten project, when it's on, it generates optimized code for each and every task on the fly instead of using the generic functions, like over here. But again, the benefits of all those free optimization mechanisms in Apache Spark architecture, we will appreciate only once our data will get big. And we are at the end of introduction to Apache Spark architecture. Congratulations, we have learned a lot of new concepts, and some of them were not really easy. The most important step is to practice. Every time you write a query, just try to open Spark UI and try to figure out what's happening under the hood. Meantime, don't forget to subscribe to the channel because there is a lot of new cool content coming shortly. Welcome everybody in Delta Lake tutorial / course because it's really deep. My name is Emil Kaminski, and let's start this video by talking for whom it really is. Stable, very simple. Overwrite, don't, and moving takes really a lot of time. Instead of that, we're starting to work on the data, the data log, but just the very sophisticated significant since I've been working on it. Often people who are preparing to get into systems or who are still studying for a degree or who haven't had their first experience yet or whose first day experience is very limited to a specific scope, for example, programming something, uploading a certain piece of code, doing some data analysis, well, they may not have really come face to face with this reality yet. But systems in production are very different from what we think of when we write a tutorial, when we're learning. And that's not a bad thing. That the didactics for learning are one thing, the pedagogy is one thing, and then what happens in the real world is another thing. It's a dissidence that occurs because you have to make an abstraction so that that someone can learn how they work. But that doesn't mean it's not good to have an idea or a taste of what things are really like and what to expect when you're working on an application that's in production. You're working on something that has users, that have queues, that has services, that has deployments, that has CIS. All of that is very different from what we learned when we were in college and we have to get into a program and we make an application that has a database and an endpoint, but it's not the same as what happens when you're in production. In production, there are deploys, there's old data, there are time cache invalidations. So there are a lot of components that when you are testing in your local lab, when you're on your personal computer, you don't see, end up encountering because, well, the things that you don't encounter because you're not exposed to real users, to real APIs, and that's not a bad thing. And that's not a bad, as I said, for learning, it's actually beneficial to abstract yourself from all of this noise. But I want to show you a little bit, without obviously exposing data from my company due to compliance and my responsibility, but with production system dependency of how your services are doing. Some responsibilities in software architecture, but I am also in a certain way a cloud provider. There is, I ensure the security operation. It goes wrong, when a deployment goes wrong, and I go to look at the logs. I find that sometimes the code to control or even uncontrollable. So for this, I prepared some material for you, some material on how, for example, some logs that I read about every day look. What you see here is not very difficult. It is not very different from what I see in CloudWatch when I go to see, for example, the SS, the ECS, or the containers, or when I see how an API is working with an ECU, I do not do this merge request. That method was used. Those are blob, yeah, they are fake, but it is a fairly illustrative example because I see something like this every day. In fact, many times I see it from the WS console or from the terminal. In this case, I opened it from set so that the error failed. Until I come to see the logs, I basically have no idea why something could be failing. Also, it's a policy not to expose so many errors like I don't know the error pad and so on because nothing like in pen testing is not. I mean, the first thing they ask me in pen testing is that it's not so visible, that is not so transparent how the system works because if not, dog, you could be exposing some critical positions and so on. So as you can see, something like this is what I see in the CloudWatch console when I go to see an API and error. If you want, we can read it a little, discern it a little to tell you more or less what each thing means. When I look, the first thing I see is a timestamp, for example. Many times in systems, if you are, for example, testing locally, you do not let the info be printed because it is not log lab or even a local server.
Once you know the tag, which is probably the first thing I look at in addition to the time, is you have the services pointing to the gateway, the service, the card is the payment service, the payment service aroma. So you can already know what failed with in worker file, like the abstraction that was carried out, like what you logged in. What was the request ID? This is a way of interpreting starting for action. For example, in the database, saying which request this action was performed. But also data that can be variable. Here, for example, in the case of an app with a logo, it's parameters that are usually always the same and then vary depending on what you are wanting to log or record or see. Then I put together a small dashboard, nothing interesting other than that. All logs that we had and with data, Starbucks many resources are they provisioning for the application to enter a bottleneck. And you get some raw, such as the peak latency, what time you have the highest peak latency, what time are the most users connect. In this case, like when you're talking about a payment application, then this is as you see the queue for dip, it's like nothing. That varies. Happening in real time. Of course, it gives me summary and in others that may be a little more harmless or that you may be interested in knowing about as a developer. But move them, since there is a lot of latency in the checkout, they're not, you will be able to solve this relatively. But you will incur failures. It is just as good to have a lot of alerts, and it can also give you this is a bad example of an alert, because if you are not transparent with the failures, that's something that you cannot handle directly, but if you can handle them and you are not being transparent about what is happening, then you are taking information from yourself in order to debug the problem or solve it. A good example of an alert is one that has a concise message. A flood of information is also not good for logging in. You need precise information. That is why alerts go beyond logging in, which is the entire history. It is like something that you should only receive if it is important. Because if you flood yourself with these alerts, well, you will lose the information. It is just as good to have a lot of information. It's just a happen to errors, which is errors with how the queue grows, and then a circuit breaker is activated. The serum certainly recovers every. Well, that's something that can happen if it's done well. It could happen without you realizing that this happened, and then when you look at it again, you realize there was a crack with a circuit breaker is activated, and the serum certainly recovers every. Well, that's something that can happen if it's done well. It could happen without you realizing that this happened, and then when you look at it again, you realize there was crash at one point, and that there were some users who suffered theft of data for a few minutes, but that the system, since it did auto health and auto call and recovered and recovered automatically. Okay. And on the other hand, I want to talk to you a little bit about this, how a real production application is structured. Because it's not as simple as nothing. I expose the API or I expose the application and the users enter there and have fun. When you have something a little more complex, you have to be talking about other types of abstractions. You have a user who's the real traffic, we agree on that, but it doesn't directly hit the API. It hits a load balancer. The load balancer distributes the request set among the active instances that are listening to respond to the API. This can be for different reasons. One of them is to balance the load. It could also be that some hit the city and others hit the IP directly because they are closer. Well, you can also balance out the load balancer. You can have international, national traffic divided between two different loads invalidating cache. So if the API already hit the cache, then it can retrieve it instead of making it another request. Step by step. So share the slide or share the screen. Whatever. I mean, yeah, your screen. Oh. All right. Okay. Welcome everyone. I see people trickling in. It's sort of an awkward time, by the way, so I expect most of the views will come from like the from regular YouTube. But like, thank you everyone for joining on this like last minute broadcast, and thank you to Ben and Sean for humoring me for this like last minute talk. This is basically introducing like a new challenge that we've been cooking up, and this is a collaboration between like some stuff I've been doing at my day job at Corrado and by Ben and Sean at Build Research and a couple more folks. The interesting thing about this is this is a new challenge that we have in the server. It's already open for submissions today. It's primarily a model architecture and optimizer competition that we've really made sure is easy for both for humans and agents to participate in. It's also a fairly nasty test, and that'll remind you that like inductive biases matter. That maybe transformers as they are don't really like work for all sorts of tasks. So I'm really honored that Ben and Sean are here to talk to us about it. So they'll go over some of the theory, and Sean will give you a demo of how to make your first submission. And this is really meant to be an interactive Q&A type session. So if you have any questions, feel free to drop them in the chat. I'll make sure to interrupt the speakers. So yeah, without further ado, Ben, please take it from here. Yeah, thanks a lot, Mark, and yeah, thank you everyone for coming. I don't know that I can see the chat with I'm joining screen, so yeah, feel free to interrupt me. Yeah, so what I want to talk about today is this competition that we're doing together with the great folks at Core Automation, which is kind of like branded one layer deeper. And the goal of the competition is to sort of see whether or not models can perform deeper computation than they were trained to do. And so in order to do this, we needed to divide like particularly tricky tasks. So here's like a quick outline. I just want to go over quickly like why serial computation matters at all. Some previous ideas in the space that have kind of like influenced how we think about things. Why depth in its own right can be difficult to evaluate, and how there are kind of confounders there. The specific task that we settled on, which is this like repeated modular squaring task. The design of the competition, how you guys can all participate, and then solicitation of community feedback. Okay, so why do we even care about serial computation at all? Well, it's really because for problems that are like inherently sequential, depth is really what at the end of the day limits difficulty. So harder instances of certain problems are just going to require longer algorithms. And so if we just train models to be only exist at some fixed depth d, then if I present you some instantiation of the problem such that more than d steps are taken, you just your model won't be able to solve it. And we also kind of don't want to
spend too much depth or too much computation if we don't need to. So we also want to do this adaptively. So basically, if the problem is hard, we should spend more computation. We should kind of like have a deeper model. And then if the problem ends up being easier, then we don't actually need like a particularly deep model or deep computation. What should like a model be able to do? Basically, it should be able to solve things step by step. So we want to actually be able to like chain long dependent steps together. It should do this adaptively. So if the things are harder, it should spend more computation. And then we want to be able to solve problems that are harder than the problems that we trained our model on. So in particular, like if we have some training data consisting of a bunch of problems that we actually like know how to solve, that's not really all we want our models to be able to do. We also want our models to be able to solve problems that like we humans don't necessarily know how to solve. So we want the models that we train to be able to use more steps at testing than they were trained to do during train time. And then finally, because all of this is kind of hard and potentially brittle, we want this training to actually be stable. So it should be reliable if we're doing like long training processes. So it's not like particularly new that hard reasoning improves with more compute. So there's this like famous graph from the OpenAI O1 paper, which is sort of showing that when it allocated more test time compute to O1, its AME performance rose. One of the key differences though between this and what we're going to focus on in this competition is that this was sort of like adaptive computation in token space. So it would kind of like verbalize more chain of thought tokens before it would solve the problem. Whereas so it would kind of like verbalize more chain of thought tokens before it would solve the problem. Whereas our particular focus is actually doing adaptive compute in late space. So like through something like looping. I'll just briefly go over our particular. Particular focus is actually doing adaptive compute in late space. So like through something like looping. So I'll just briefly go over some prior work. More compute can actually mean a few different things, and we're kind of going to focus on the third thing. But one way in which you could actually spend more compute is to do sort of like more parallel sampling. So instead of just generating like a single alternative, you could generate a bunch of alternatives through like lots and lots of like parallel sampling. You could do sort of like visible serial computation, which is I kind of mentioned in the O1 case, where you sort of extend the chain of thought. Or you could do this kind of in latent space. So you could do like more recurrent updates, more looping, and generally like repeated computation within the model. And this is kind of like a recurring idea. So all the way back in like 2016, there was like Graves's adaptive computation time paper, where kind of like a halting probe was learned. So the model could think for longer, and it would kind of figure out the ideal amount of time to think subject to some sort of like thinking time penalty. Then there's the universal transformer line of work, which is you take some transformer, and it has like some number of layers and some number of parameters, and you kind of like repeat these blocks. So you don't actually increase like the number of parameters in your model, but you sort of like increase the effective depth by allowing like different layers to loop more. Then there's kind of these like easy to hard iteration extrapolation line of work, especially from like Tom Goldstein's group, where you train for a certain number of iterations, but then at test time you allow yourself to go for longer than that. And then most recently, work, for example, that Sean has worked on is something related where you train transformer blocks for a certain amount of train time, and then at inference time you allow yourself to go far this. And I guess just like stressing again the points of like where 6-step models can fail is if you have an easy, medium, or hard inputs, you're going to have exactly D updates. So the specific update will be different whether it's easy, medium, or hard, but you're only allowed, say, like D state updates if you have like D layers in the model. The whole idea behind adaptive computation time, whether it's easy, medium, or hard, but you're only allowed, say, like D state updates if you have like D layers in the model. The whole idea behind adaptive computation time is that you repeat some number of times, and then you predict like the probability with which you should halt at that point. And then once you've kind of like accumulated a sufficiently large probability, then you halt. So the idea being that different inputs, if they're harder, will have like a lower halting probability over time. And so it will actually take the effective depth of the model will be larger. And this sort of comes at a cost. If the model could think for as long as it wanted without any penalty, it might just like think forever. So you also want to discourage unnecessary updates, and that's what the sort of like ponder cost penalty is. So more updates might improve the answer, but you don't want to do so many that your sort of like aggregated loss is too high. And what they found empirically was actually that as the difficulty of the problem increased, the ponder time also increased, but then it's like really like blow up, precisely because of this sort of like regularization penalty. Then the idea behind universal transformers, as I mentioned, is to sort of just reuse the same block. So the number of parameters stays fixed, but the recurrent depth grows. And then the whole idea behind this like recurrence extract, sort of just reuse the same block. So the number of parameters stays fixed, but the recurrent depth grows. And then the whole idea behind this like recurrence extrapolation is at train time, you say like have some number of recurrent iterations k, and these are like the easy inputs. And then at test time, maybe you have harder inputs, and then you'll have like more than k iterations. Like there's so it's the same weights, but one iteration is going to like reuse the same block. So for example, for like the prefix sum task, maybe you train on like 32-bit strings for 10 iterations, but then at test time you do like 40 or 44-bit strings, and now you can do like between 10 and 16 iterations. And you can basically
Yeah, this seems like a good competition. So next task is we will prepare for this competition. Tomorrow we will go through this video. We'll look at the ACT paper, adaptive computation paper. That is the task. Tasks. right? Go through B A C T paper adaptive computation.
We find that at least on this task, as you sort of increase the difficulty, we use the same. Yeah. So and one iteration is going to like reuse the same block basically. And yeah. So for example, for like the prefix sum task, maybe you train on like 32-bit strings for 10 iterations, but then at test time you do like 40 or 44-bit strings, and now you can do like between 10 and 16 iterations. And you can basically find that at least on this task, as you sort of increase the difficulty, as long as you also increase the number of iterations you're allowed, the accuracy rises. And there's this like really nice like visual maze example where you train on mazes that are like kind of small, then the model actually like learns the general like algorithm to solve these types of mazes, such that if you increase the size of the maze, but the sort of like type of maze is the same. And actually at test time, you do see this like nice generalization. More recently, there's been work on sort of serial reasoning in latent space. So instead of like verbalizing, i.e. like emitting some new like chain of thought token, you actually just continue looping in latent space. And maybe I should say like the reason why this is so attractive from a theoretical perspective is that there's this idea that actually if you can do adaptive computation in latent space, then you can sort of simulate chain of thought. So you should actually be strictly more expressive if you can do this like latent space style adaptive reasoning rather than token level adaptive reasoning. And this kind of makes sense as well intuitively, because if you can do this sort of latent level adaptive reasoning, you are like allowing your model to continually manipulate this like continuous quantity, this like vector in Rn. Whereas if you're doing the adaptive computation in token level space, you're kind of like every forecast or something like forcing yourself to do this like discretization step, which is somewhat artificial. Yeah, and like similar idea here, you have like a transformer core, so to speak, that at train time you sample the number of recurrences that you want, and then at inference time you allow yourself to actually like increase this shared core that you loop over and over again. So this prelude block in some transformer model is not looped. This like actual prediction block is not looped, but then this kind of like shared thinking block or like set of blocks is actually looped some number of times, and it's different at train time than test time. And what's Sean and his collaborators found basically is that as you like increase the number of recurrences, you can improve accuracy at least on tasks that seem like they model something like serial computation. Okay, you can improve accuracy at least on tasks that seem like they model something like serial computation. Okay, but why can like depth actually be hard to evaluate? So there's a few things that fuses errata that you might want for a depth benchmark. One is that it should actually be serial. So we don't want something that is actually a shallow task in disguise. And in particular, like there's a difference between a method. it being serial and a task itself being serial. And I'll give an example of this in a moment. Then some computation can sort of be masqueraded as memorization in disguise. So one way of like one example here is you might have some task that like maybe that task itself is serial, but if you allow your models to be large enough, then the model can basically just like memorize a lookup table such that it's not actually really doing any serial computation at a certain point. It's just sort of like retrieving what it believes is the correct answer from this lookup table that it's built out. And then this last point, I think is like really key. This depth extrapolation idea that some of these prior works also touch on is we really want the test instances to require more depth than training. So it's not enough that's like the test that actually comes from the exact same distribution as the train set. We want it to be strictly ordered because we really want to sort of like model this idea of like having models that can discover things or do things that like we humans might not know how to solve. Yeah, so as I mentioned, a serial procedure does not imply a serial problem. So it is not enough to like have a particular method that is not shallow. We want the actual task itself to not be shallow. So for example, we want the actual task itself to not be shallow. So for example, if you're computing the greatest common divisor, there's a very serial way to do this. You start with your like number A, and then at each step you compute the remainder. So you can compute these terms like R1, R2, so on and so forth up to RK. And in order to get like RK, you need to like previously compute like R1 through RK minus 1. But computing the GCD itself is actually not a serial task. So like one way to just brute force it is I hand you some number, I ask you what the GCD is, and you just sort of brute force compute like all numbers less than or equal to that number and determine if that is like a divisor, and then you just choose the one that is the largest. So the Euclidean algorithm is serial, but the computation of the GCD does not have to be. And yeah, kind of this idea that I mentioned before, we also can have like memorization that sort of like masquerades in the sense that you might actually have some function such that if your model is large enough, it just learns some lookup table, and then at test time, it just like interpolates there. Yeah, and finally, again, we just want training and test steps to be separable. So test should be harder than train, and we should have some like very like nice granular dials that like we can actually adjust this. And so this task that we settled on that kind of like satisfies all of these desiderata is this like repeated modular squaring task. How does it work? We hand you some number x, and then we hand you some modulus n and some other positive integer t, and we ask you to compute x to the 2 to the t mod n. So concretely, you do x squared, x to the fourth, x to the 8, so on and so forth. And then we just ask you what are the digits of y mod n. So why is this nice? You do x squared, x to the fourth, x to the 8, so on and so forth. And then we just ask you what are the digits of y mod n. So why is this nice? There's no shortcut. In fact, it is sort of I can't remember if it's conjectured or actually proven that sort of like the best you can do is like log t torrents. And like on our end, we can actually force this depth extrapolation by like at in the sort of train set, we hand you guys a certain like n and t. But then at test time, we can actually like increase t, for example. And then since the whole point of this competition is to run everything on one GPU, if we on our end choose n and p in a nice enough way, it should prevent memorization of the model. So concretely, how does this work? If we have n equals 77, x equals 2, and t equal 4, so that means x naught is equal to 2, x1 is 2 squared, which is 4 mod 77, x2 is 4 squared, which is 16 mod. Mod 77. X cubed is 16 squared, which is 256, but mod 77, that's 25. And then 25 squared is 625, but mod 77, that's 9. So then you would be presented basically 2, 4, and 77, and the answer would be 9. And so this is the same computation, but the idea basically is that if you get one part of this wrong, you are it's kind of like irrecoverable. The answer is just going to be wrong if you get like any of these like individual squarings incorrect, as long as we've chosen n sufficiently well. And the idea basically is that you really needed the exact value of x and k. So actually, like for people that like number theory, this is not like 100% true. For example, if we chose n very poorly and we chose x very poorly, then this would kind of be a boring task. So for example, if we chose like n equal to 8 and then x was odd, then the squares would basically at a certain point just all be 1, and you wouldn't really need to do anything. But we're going to choose n to be like some semi-prime, such that the two shortcuts are kind of blocked. So the obvious shortcut is to just like tabulate the entire function. But as long as we choose n sufficiently large, this is not possible. And then the other thing is, I guess, like coming from number theory, instead of computing x to the 2 to the t mod n, there's this like trick, which is basically Lagrange's theorem, which instead of doing x to the 2 to the t mod n, what you can do instead is x to the 2 to the t mod 5n, where 5n is the totient function, so the number of integers co-prime to n. But this relies on knowing the factorization of n. And as long as we hide this, i.e., we don't show you the factorization, it's very difficult. So that's all this idea is that 5n is if n is semi-prime, meaning it's just a product of two distinct primes, then the number of co-prime integers to less than n is just p minus 1 times p minus 1. But in order to sort of know that, you need